Here is something that should bother you a little. And then, I promise, will start to feel like the most peaceful thing you've heard all week. The nearest large galaxy to ours is already touching us. Right now, tonight, in the dark between us and everything else. You can't see it, you can't feel it, but it's there, 2.5 million light-years away. And the two of them have been reaching toward each other for longer than the Earth has existed. Their outermost edges, made of something invisible and ancient, are almost certainly overlapping as you lie here. That's where tonight's story begins. My name is not important right now. What matters is that you're here, and I'm here, and somewhere above whatever ceiling is over your head, the universe is doing things it has been doing for 13 billion years quietly without asking permission, without waiting for us to notice. Welcome to Sleepy Science Stories. Before we go any further, where are you tonight? Maybe you're in a bedroom in a city where the sky never quite goes dark, where the closest thing to stars you'll see tonight is the blinking red light of a plane crossing somewhere overhead. You've gotten used to a sky that glows orange at the edges. You've stopped looking up. Maybe you're somewhere quieter, a house outside of town, where on a clear night in autumn you can actually see the Milky Way. That faint, impossible smear of light that crosses the sky like something spilled and never cleaned up. If that's you, you already know the feeling we're chasing tonight. Or maybe you're somewhere in between. A guest room, a hotel, a place that doesn't quite feel like yours yet. You opened this video the way you might crack a window, not because you're hot, but because you needed something to come in. Wherever you are, you and I are sharing this moment right now. Across whatever distance sits between us, and after tonight, you'll have a new sense of what distance actually means. That's real. That matters. Tonight's question is a simple one to ask, and an almost impossible one to fully answer. How far apart are galaxies? Really? Not the number. Numbers at this scale lose their meaning after the first syllable. 1 billion light years. 1 trillion. The mind goes quiet and moves on. What I mean is the feeling of it, the texture of that distance. What's actually in it? Whether it's growing, whether somewhere out there is a place so empty that if our entire galaxy sat at its center, all 400 billion stars of it, we might never have discovered the rest of the universe existed. There is such a place. We'll get there tonight. We'll start with that galaxy that's already touching us, and learn why the collision that everyone says is coming may not be as certain as we thought. We'll find out what actually fills the space between galaxies, because it isn't nothing. Not exactly. We'll trace the largest structure we belong to, one that only received its name 11 years ago, and that recent research suggests may itself be just a smaller piece of something 10 times bigger. We'll stand at the edge of a void so large that astronomers named it the Great Nothing, and we'll end at the farthest thing human eyes have ever seen. A galaxy so distant that the light reaching us right now left its source before our sun existed, before our solar system, before almost everything we know. It was confirmed just last month. Its name is MOM Z14. One small thing before we begin. If these quiet journeys through science help you rest, consider subscribing to Sleepy Science Stories. It takes 2 seconds, and it helps other people who need a place like this find their way here. One restful night at a time. Now, let your shoulders drop. Let your jaw unclench. If it's been holding on to something today, let your breath slow. Not forced, just allowed. You don't need to remember any of this tomorrow. You don't need to follow along carefully. You don't need to do anything at all. Just let the story come to you. The galaxies have been waiting in silence for longer than we have words for. And tonight, gently, slowly, we're going to find out how far apart they really are. Let's start somewhere familiar, not with galaxies, not yet. Let's start with a step. Right now, if you wanted to get up and walk to the kitchen, maybe 10 steps, maybe 20, depending on where you are. You'd cross a distance your brain understands completely. It doesn't need to calculate. It just knows 20 feet, 30 feet. The body navigates it without thinking. That understanding, that felt sense of distance, is one of the most useful things the human mind does. We measure the world against ourselves, against our stride, against the time it takes to get somewhere. But what happens when the distances become too large for the body to feel? That's what tonight is really about. Think for a moment about the longest drive you've ever taken, or the longest you can imagine. New York to Los Angeles, roughly 2,800 miles. 3 days if you push it, more if you stop to sleep, which you should. You pass through time zones. The landscape changes completely, from dense gray highways to flat plains to desert to mountains to coast. By the time you arrive, you have a physical memory of how far you've gone. 2,800 miles is a number the body can hold. Now, the moon. The moon hangs above us every night, close enough to see its craters with binoculars. Close enough that for most of human history people assumed it was reachable, if only you could get high enough. It looks like it's just up there. The moon is 855 miles away. That's not 2,800. That's 85 drives from New York to Los Angeles, back to back without stopping. If you drove at highway speed, 65 miles an hour, no brakes, no sleep, you would arrive at the moon in roughly 5.5 months. And the moon is the closest large object in the sky. Now the sun, 93 million miles. That number needs a moment to land. If you drove to the sun at 65 miles an hour, non-stop, no traffic, some kind of impossible highway extending through space, the trip would take about 163 years. You would need to have started in the 1860s to arrive today. Abraham Lincoln would have waved you off. But here's the thing, light doesn't drive. Light moves at 186,282 miles per second. And even at that speed, the fastest speed anything in the universe can travel, it still takes sunlight 8 minutes and 20 seconds to reach us. 8 minutes and 20 seconds. That means the sunlight warming your skin on any given afternoon left its source while you were still doing something 8 minutes ago. The sun you see is not the sun as it is, it's the sun as it was. This gap between seeing and being, between light leaving and light arriving, is something we'll come back to tonight, because at galactic distances, it becomes everything. Now step back a little further, past the sun, past the planets, out through the outer edges of our solar system, past the orbit of Neptune, past the scattered disk of icy objects at the very fringes, out into the deep quiet beyond. Here's where miles stop working, not because they're wrong, but because the numbers become so large, they stop meaning anything. The distance to the nearest star, A small, dim red dwarf called Proxima Centauri is approximately 25 trillion miles. Say that number out loud. 25 trillion miles. It doesn't land. The mind just shrugs and moves on, the way it does with very large numbers that have no anchor in experience. So astronomers use a different unit. Not miles, not kilometers, light years. A light year sounds like time. It isn't. It's distance. The distance light covers in 1 full year of traveling at 186,282 miles per second. That works out to just under 6 trillion miles. About 88 trillion, if you want the precise number. 1 light year, 6 trillion miles. It's still an enormous number. But it becomes useful when distances are even more enormous, because instead of saying 25 trillion miles, you can say 4 light years. And that phrase carries something the number doesn't. It carries duration, a sense of light in motion, of something traveling relentlessly across the dark. Proxima Centauri, the closest star to our Sun, is 4.24 light years away. Light from Proxima Centauri takes 4 years and 3 months to reach us. Right now, some of that light is partway here. Some of it left when you were 4 years younger, and it's still crossing the gap. And Proxima Centauri is our nearest neighbor. Here's where the numbers start to shift in a way that matters. Our galaxy, the Milky Way, is approximately 100,000 light-years across. A disk of stars, gas, and dust, thin as a frisbee relative to its width, roughly 1,000 light-years thick at the spiral arms and wider at the center. Our solar system sits about 27 light-years from the galactic center, not at the core, not at the edge, but somewhere in the quieter outer suburbs, on a minor spiral arm called the Orion Arm. If the Milky Way were the size of the continental United States, our solar system would be a speck roughly the size of a single period on this page, somewhere around Kansas City. 100,000 light-years, the time it takes light, the fastest thing in the universe, to cross our galaxy from one side to the other. If a civilization on the far side of the Milky Way sent us a message today, traveling at the speed of light, we would receive it in the year 101,025. Now, here is the thing that changes everything about tonight. Our galaxy is enormous. It contains somewhere between 100 and 400 billion stars. It has been forming stars for over 13 billion years. It is, by any measure, a staggeringly large structure, and it is just one galaxy, among an estimated 2 trillion in the observable universe. 2 trillion. The Milky Way is not special in its scale. It is an ordinary spiral galaxy, mid-size, moderately active, unremarkable by the standards of the cosmos. The kind of galaxy you'd scroll past in a catalog without stopping, and between the Milky Way and its nearest large neighbor, between us and the galaxy you can see with your naked eye on a clear autumn night, there is a gap measured not in miles, not in the length of a road trip, not in the years of a human life. A gap measured in millions of light years. That gap, what fills it? Whether it's truly empty, whether it's growing, that's what we're here to find out. The distance we've covered tonight, from your bedroom to the edge of the Milky Way, is just the first step. The real distances haven't started yet. Before we go any further out, let's stop here for a moment, right where we are, in our own neighborhood, because here is something worth sitting with, before we cross into the truly vast distances. The nearest large galaxy to ours is visible to the naked eye. Tonight. Right now. Assuming you're somewhere with a dark enough sky, and it's the right time of year. It hangs in the autumn sky in the northern hemisphere, just above the constellation Andromeda, a faint oval smudge of light, barely there, easy to miss, easy to mistake for a wisp of cloud. For most of human history, people who noticed it at all assumed it was simply part of the Milky Way, a local cluster of stars, not too far off. It wasn't until the 1920s that an astronomer named Edwin Hubble, using a telescope at the top of Mount Wilson in California, on a series of clear winter nights, measured the distance to what was then called the Andromeda Nebula, and realized something that changed everything. It was not a nebula. It was an entire galaxy, separate from ours, 2.5 million light-years away. A system of 1 trillion stars so distant that the light reaching your eyes on any given autumn night left its source before modern humans existed, before Homo sapiens had spread out of Africa, before the oldest cave paintings, before language, perhaps, as we know it. That faint smudge you can see on a dark night. That is a message from before our species began. The Andromeda Galaxy, also known as M31, sits approximately 2.537 million light-years from Earth. That is the most precise measurement we currently have, confirmed by multiple methods, including observations of Cepheid variable stars, which act as reliable cosmic measuring sticks because their brightness pulses in predictable rhythms that reveal their true luminosity and therefore their distance. It is the closest large spiral galaxy to our own, and it is moving toward us. Right now, at this moment, while you lie still, Andromeda is approaching at roughly 110 kilometers per second, about 68 miles per second, closing the gap, crossing the void between us at a speed that sounds large and is, in cosmic terms, patient. For decades, this fact was presented as a kind of cosmic drama, the Andromeda collision. Galaxies on a collision course, an apocalypse in 4 billion years. But here's what the most recent science actually says, and it's far more interesting than the simple story. In a paper published in Nature Astronomy in 2025, a team of astronomers led by Till Sawala at the University of Helsinki ran new simulations using the most precise data yet available from the Gaia and Hubble space telescopes. They factored in not just the motion of Andromeda, but the gravitational influence of every major galaxies in our local neighborhood, including the Triangulum galaxy and a small but surprisingly consequential galaxy called the Large Magellanic Cloud. What they found was this: the chance of the Milky Way and Andromeda actually merging in the next 10 billion years is approximately 50-50. A coin flip. The culprit making it uncertain is a galaxy you may never have heard of, the Large Magellanic Cloud, a small, irregular, beautiful smear of light visible from the southern hemisphere orbiting the Milky Way at a distance of about 163,000 light-years. Small enough to overlook, influential enough to change the fate of 2 trillion star systems. The Large Magellanic Cloud's orbit runs roughly perpendicular to the Milky Way Andromeda plane. As it moves, its gravity pulls the Milky Way sideways, introducing a wobble, a sideways momentum, tugging our galaxy just enough off course that in roughly half of all simulated futures, the Milky Way slides past Andromeda without merging. "What stands out," said astrophysicist Elena Dolnia of the University of Wisconsin-Madison, responding to the study, "is the role of the Large Magellanic Cloud. It's not just a minor satellite, it's a major player. A dwarf galaxy, barely a smudge in the southern sky, may be quietly rerouting the destiny of two galaxies, each containing hundreds of billions of stars. There is something wonderfully unexpected about that. What is certain is this: within the next 2.4 billion years, the Large Magellanic Cloud itself will merge with the Milky Way. That collision is far more assured, a 93% probability according to current models. It will be the Milky Way's next major galactic merger, arriving long before any possible encounter with Andromeda. So the drama isn't between two equal titans approaching each other from a distance. It's messier than that, more intimate. A small companion pulling the larger one off course, changing what comes next in ways that even the best simulations can't fully predict. The universe doesn't tell clean stories. Now here is something that almost never appears in discussions of the Andromeda Galaxy. And it should, because it reframes everything. We talk about the distance between the Milky Way and Andromeda as if it's the gap between two clean, well-defined objects. Two dinner plates, 25 meters apart. That image is useful, but it's incomplete because galaxies don't end where their stars end. Surrounding every large galaxy is an enormous invisible halo of hot plasma, of dark matter, of gas shed by supernovae over billions of years. A diffuse, nearly undetectable sphere that extends far beyond anything you'd see in a photograph. In 2015, scientists using the Hubble Space Telescope mapped the halo surrounding Andromeda. What they found was startling. Andromeda's gaseous halo stretches approximately 1.3 million light-years from its center, and in some directions, as far as 2 million light-years. 2 million light-years. The distance between the Milky Way and Andromeda is 2.537 million light-years. You can do that math quietly if you like. It means that Andromeda's halo already reaches more than halfway across the gap between us, and the Milky Way has its own halo, extending perhaps 1 million light-years in radius, possibly more. The dark matter halo of our galaxy alone may span nearly 2 million light-years across. As the astronomer Mike Boylan Colchin of the University of Texas put it, if you include the dark matter halos of both galaxies, Milkomeda, the name some astronomers use for whatever emerges from a merger, may already be close to forming at our furthest frontiers. The collision, in other words, has already begun. Not in the visible light you'd see in a photograph. In the dark, in the invisible, in the outermost tendrils of two galaxies reaching toward each other across millions of light-years. We are not waiting for something to start. We are already inside it. Take a moment with that. You are lying on a planet, orbiting a star, inside a galaxy whose invisible outer edge is already intertwined with the outer edge of the galaxy next door. The encounter is not 4 billion years away. It is happening right now, in slow motion in the dark, at scales that no human instrument can observe all at once. The gap between us and Andromeda is 537 million light-years, and it is not empty. It is already shared. Beyond Andromeda, the neighborhood gets quieter but not simpler. The Triangulum Galaxy, M33, sits about 2.7 million light-years away, slightly farther than Andromeda. It is the third largest member of our local group, a face-on spiral, fainter than Andromeda, harder to see, sometimes just visible to the naked eye under exceptional conditions. It too is gravitationally linked to both the Milky Way and Andromeda, its orbit in the simulations actually increasing the probability of a merger between the two giants. A counterweight to the large Magellanic Cloud's sideways pull, Triangulum was a deciding vote, quietly cast. Beyond these three large spirals, our local group is populated mostly by dwarf galaxies. Small, dim, irregularly shaped systems that cluster around the larger members like moons around planets. About 80 are currently catalogued. More are being discovered as telescope technology improves. Many are so faint they evaded detection until recently. The entire local group spans roughly 10 million light-years. A sphere containing 80 galaxies, 3 of which are large spirals. The rest quiet dwarfs scattered through the dark between them. 10 million light-years in that volume. 80 galaxies, trillions of stars, billions of worlds, and, as far as we know, one planet that has learned to ask questions about all of it. And here is the thing about the local group that matters for tonight's larger question. Even here, in our own backyard, the distances are already so vast that they resist imagination. The gap between us and Andromeda alone, 537 million light-years, is 25 times the diameter of the Milky Way, and that is a neighbor, a close one, by cosmic standards. Which means that when we step beyond the local group, out toward the clusters and superclusters and filaments and voids that make up the rest of the universe, we are not stepping into something that is more of the same. We are stepping into something qualitatively different. The local group is, in a sense, the last place where distance still feels like a relationship between things that know each other. Andromeda's halo touching ours, the Magellanic Clouds orbiting us, Triangulum tangled in the gravitational future of its neighbors. Beyond this, the distances grow cold. Beyond this, the galaxies don't touch at all. Here is something that no one quite warns you about when they talk about intergalactic distances. And I want to take a moment with it, because once you see it, it changes the way the rest of tonight sounds. Galaxies, in a very precise and counterintuitive sense, are closer to each other than the stars inside them. Not in absolute terms. In absolute terms, the gap between the Milky Way and Andromeda, 537 million light-years, is incomparably larger than the gap between our Sun and Proxima Centauri, 4.24 light-years away. But absolute distance isn't the right measurement here. What matters is relative distance, the ratio, the proportion of gap to object. And when you look at the ratios, the numbers change everything. Let's build this slowly. Start with a star. Our Sun has a diameter of approximately 865,000 miles. That's a large number, about 109 times wider than the Earth, but in the context of space, it's vanishingly small. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. That's roughly 25 trillion miles. So, the distance to the nearest star is about 25 trillion miles. The diameter of the Sun is about 865,000 miles. Divide one by the other. The nearest star is approximately 29 million times the Sun's diameter away from us. Say that again quietly. 29 million times the Sun's own width. If you shrunk the Sun down to the size of a grain of sand, a single grain sitting on a table in front of you, the nearest star at the same scale would be sitting roughly 4 kilometers away. Nearly 2.5 miles. 2 grains of sand, 2.5 miles apart, in an otherwise empty room the size of a continent. This is what the inside of a galaxy actually looks like at scale, almost entirely empty. Stars so far apart from each other, relative to their size, that the space between them is almost impossible to overstate. Now let's look at galaxies. The Milky Way has a stellar disk about 100,000 light-years across. The nearest large galaxy to ours, Andromeda, is 537 million light-years away. Divide the distance by the size. The gap between the Milky Way and Andromeda is approximately 25 times the Milky Way's own diameter. 25 times, not 29 million. Not a million, not even 1,000. 25. Hold both numbers next to each other for a moment. Stars in a galaxy, separated by about 29 million times their own diameter. Galaxies in the universe, separated by about 25 times their own diameter. The ratio for galaxies is more than 1,000,000 times smaller than the ratio for stars, which means, in the most precise, mathematically defensible sense, galaxies are far closer to each other, relative to their size, than stars are within a galaxy. The universe is not uniformly sparse. It is sparse in some ways and surprisingly crowded in others. And the level at which it is most crowded, most intimate, most prone to collision and interaction, is not the level of individual stars. It is the level of galaxies. This isn't just an abstract curiosity. It has a concrete consequence that you can hear tonight in how we talk about the Milky Way. Our galaxy has consumed other galaxies multiple times. Astronomers have found the remnants, stellar streams, star populations with unusual chemistry, orbits that don't quite fit, scattered throughout the Milky Way's halo like the bones of meals eaten long ago. The Sagittarius dwarf galaxy, for example, is currently being torn apart and absorbed by the Milky Way as we exist. Stars from it are being pulled into long ribbons around our galaxy right now, quietly, over millions of years. Between 5 and 25% of all galaxies in the observable universe are currently in some stage of interaction or merger with another galaxy, according to astronomers' best estimates from Hubble survey data. One study found that large galaxies, on average, merged with another large galaxy approximately once in the past 9 billion years. Small galaxies merged with large ones 3 times more often. These are not rare events. They are the normal biography of a galaxy. The Milky Way did not grow by accumulating gas alone. It grew by eating. Now here is where the analogy breaks down beautifully and becomes something worth holding on to as you drift. When 2 galaxies merge, the stars inside them almost never actually collide. Think about that. 2 systems, each containing hundreds of billions of stars, pass through each other. And statistically, not a single star needs to directly strike another. Because even though galaxies are relatively close together, the stars within them are still fantastically far apart. Those 29 million diameters we calculated. 2 galaxies can interpenetrate completely, pass through each other like two clouds of fog, and the individual stars simply slide past one another in the dark. What does collide is the gas, the enormous clouds of hydrogen and helium drifting between the stars. Those slam together, compress, heat up, and trigger enormous bursts of new star formation. A galaxy merger is not a destruction. It is more like a birth announcement, sometimes violent, always creative. As one description puts it, when galaxies collide, their stars pass through each other. What collides spectacularly is everything between them. Let's ground all of this in something you can picture. NASA has a scale model that compares stars to galaxies on the same terms. Here's what it says. Confirmed. The ratio between a sun-like star's diameter and its distance to the next neighboring star is about 1 to 10 million. The separation between our Milky Way and Andromeda is a ratio of only about 1 to 25. That is a difference of 400,000 times. Not 400,000%. 400,000 times. Another way to see it. A lecturer at Ohio State University once described it like this. Imagine building two scale models. In the first, you represent each star as a ping-pong ball. At that scale, the distance from our Sun to Proxima Centauri would be over 1,000 kilometers, roughly the distance from Columbus, Ohio, to Jacksonville, Florida. Now build the second model. Represent each galaxy as a ping-pong ball. At that scale, the Milky Way and Andromeda are sitting 1 meter apart, about 3 feet. Two ping-pong balls on the same table. Same object, a ping-pong ball, representing two completely different scales of reality. But the difference in how close they sit to each other tells you everything. This is the thing that no one says clearly enough about intergalactic space. It is not that galaxies are lonely islands in a vast, impassable ocean. It is that galaxies are the level of the universe at which things actually find each other. They are the scale at which gravity wins. The scale at which encounters happen, mergers happen, stars are born from collisions of gas, histories become entangled. Below that, at the level of individual stars, the distances are so enormous that stars almost never touch. The universe at that scale is nearly sterile in its emptiness. Above that, at the level of galaxy clusters and superclusters, the distances grow large again, though still structured by filaments and nodes. But right here, at the galactic scale, this is where the universe gets relational. This is where things know each other. So when we ask how far apart galaxies really are, the answer, it turns out, is not as far as you might expect. Not relative to what they are. Not relative to the alternative. A galaxy is a city, and the distance to the next city is about 25 times its own width. That is a landscape you could, in principle, navigate, given enough time, given enough gravity. And gravity, out here, has all the time there is. When we say the space between galaxies is empty, we are not being fully honest. Emptiness, it turns out, is one of the most misleading words in the astronomical vocabulary. We use it to describe the voids between galaxies, the way people once used it to describe the ocean floor, as a shorthand for beyond reach, beyond knowing, therefore beyond interest. But the ocean floor turned out to be one of the most intricate, alive, and strange environments on the planet. And the space between galaxies, it now appears, is not empty either. It is the hiding place of more than half the ordinary matter in the observable universe. Let that sit for a moment. More than half of all the normal matter, the kind made of protons, neutrons, electrons, the kind that makes up stars, planets, oceans, and you, is not in galaxies. It is drifting in the space between them, in a form so thin, so hot, so difficult to detect that for decades astronomers couldn't find it at all. They called it, with a kind of dry scientific frustration, the missing baryons. It wasn't missing. It was hiding in plain sight, in the gap we thought was nothing. Here is what we now know is filling the space between galaxies. The intergalactic medium, or IGM, is a vast, nearly invisible ocean of gas that permeates the entire universe between galaxies. Its average density, measured by Harvard Center for Astrophysics and confirmed by multiple independent studies, is approximately 1 atom per cubic meter. 1 atom per cubic meter. To feel how thin that is, the air you are breathing right now contains roughly 27 billion atoms per cubic meter. The intergalactic medium, by comparison, contains 1. A single atom, adrift, with about a cubic meter of emptiness on all sides before the next one. The best vacuum humans have ever created in a laboratory, using extraordinary machines, sealed chambers, and every technological trick available, contains roughly 100 billion atoms per cubic meter. The intergalactic medium is hundreds of billions of times less dense than the best vacuum we can make. And yet, it is not empty. It is just incomprehensibly thin. Now here is where it gets stranger. Despite its thinness, the intergalactic medium is extraordinarily hot. The warm-hot intergalactic medium, which makes up the filamentary structure connecting galaxy clusters, reaches temperatures of roughly 10 million degrees Fahrenheit, or about 5 to 6 million degrees Celsius. A new study published in Astronomy and Astrophysics in late 2024, using data from the first Erosita All-Sky X-ray survey, confirmed these temperatures directly, measuring the gas across hundreds of sight lines through intergalactic space for the first time at this scale. 10 million degrees Fahrenheit. That is about 6 times hotter than the surface of the Sun. The gas between galaxies is one of the hottest things in the observable universe, and yet you would never know it if you were floating in it, because despite its temperature, defined by how fast its individual particles move, the gas is so utterly sparse that it carries almost no heat in any practical sense. Temperature is not the same as heat. A single particle moving very fast has a high temperature, but carries almost no energy you could feel. The intergalactic medium is technically on fire, and completely undetectable to any sense you possess. A furnace with nothing to burn. This raises an obvious question. If it's so thin and so hot, how did astronomers find it? The answer involves one of the most elegant techniques in modern astrophysics, and it begins with quasars. Quasars are the brightest objects in the observable universe, the hyperactive cores of distant galaxies, powered by supermassive black holes consuming matter at extraordinary rates, blazing with light across billions of light years. They act, for astronomers, as cosmic flashlights. When you shine a flashlight through fog, the fog absorbs some of the light in characteristic ways that depend on what the fog is made of. Similarly, when quasar light travels through the intergalactic medium on its way to our telescopes, the gas absorbs specific wavelengths leaving dark lines in the spectrum. These lines are called the Lyman alpha forest, a series of thin, dark marks imprinted in the quasar's light by every cloud of hydrogen the light passed through on its billions of light-year journey. Every line is a scar. Every scar is a record of something the light encountered in the dark. Astronomers can read these lines the way a geologist reads rock layers, as a layered history of everything between us and that distant source. The position of each absorption line tells you the distance to that cloud of gas. The depth of the line tells you its density. The slight shifts tell you its temperature and its velocity. A beam of light from a quasar 10 billion light-years away arrives at our telescopes, carrying a complete diary of everything it passed through. We never had to go there. We just had to learn to read. In 2018, using the XMM Newton X-ray Observatory and the Hubble Space Telescope, a team led by Fabrizio Nicastro detected the signature of highly ionized oxygen, OVI, at two distinct locations along the line of sight to a quasar called 1ES 1553, located more than 4 billion light-years away. The oxygen was sitting in the warm, hot intergalactic medium, in the filaments connecting galaxies. Its abundance matched, within measurement uncertainty, the amount of matter that had been missing from the baryon census for decades. The paper's conclusion was unusually direct for a scientific journal. We conclude that the missing baryons have been found. In November 2024, a new study using the Erosita All-Sky Survey provided the most detailed map yet of this material, tracing WIMS filaments across hundreds of galaxy clusters and pairs. The team estimated that the WEM between galaxy clusters could account for as much as 20% of the universe's missing baryons, with more to be found as surveys improve. The story is not finished, but the gap in the baryon census, which haunted cosmology for decades, is closing. And what it reveals is this: the space between galaxies is not a void that matter has avoided. It is where matter went when galaxies were born, expelled by supernovae, pushed out by the jets of black holes, dispersed over billions of years into the enormous spaces between. The intergalactic medium is, in a very real sense, what galaxies breathed out. There is one more layer to this story, and it may be the most beautiful. The intergalactic medium is not uniformly distributed. It follows a pattern, the same pattern that organizes galaxies themselves. The cosmic web, in the voids, the great bubbles of near emptiness that make up most of the universe's volume. The IGM is at its thinnest and coldest, a few degrees above absolute zero, almost nothing. But along the filaments, the threads of the cosmic web that connect galaxy clusters like silk connecting dewdrops, the IGM is denser, hotter, more turbulent. This is the WIM, the warm, hot phase, concentrated along the skeleton of the universe, heated by the gravitational energy of matter falling inward along those enormous threads. And at the nodes, where filaments intersect, where galaxy clusters gather, the gas is hottest of all, compressed to temperatures of tens of millions of degrees, glowing in X-rays that telescopes like Chandra and XMM Newton, and now Erosita, have learned to read. The structure of the intergalactic medium is, in this sense, a ghost image of the structure of everything. It fills the same shape as the cosmic web. It connects the same dots. It simply does so invisibly, in the dark, at temperatures that have no analog in human experience. The space between galaxies is not empty. It is the outline of a structure we are only now learning to see. Think about what that means for the distance between us and Andromeda. That 2.537 million light-years of gap we talked about earlier. It is not truly a gap at all. It is threaded with gas, thin enough that you would float through it without knowing it was there, hot enough to be technically on fire, ancient enough to carry the signature of Big Bang nucleosynthesis. Hydrogen and helium forged in the universe's first 3 minutes, drifting ever since, waiting for a quasar somewhere to backlight it so we could finally read its history. And somewhere in that material between us and Andromeda, the two dark matter halos we discussed are already overlapping. The gas is already mixing at the outermost edges in ways no photograph could capture. The encounter that the visible universe says hasn't started yet is already, at this invisible level, well underway. Tonight, as you rest here on this small planet in the outer edge of one spiral galaxy, the gas is out there, 1 atom per cubic meter, 10 million degrees, moving at hundreds of kilometers per second in all directions, not waiting for anything, not going anywhere in particular, just drifting, as it has for 13 billion years. Through the space between things, the universe is not empty. It is just quiet. Galaxies are not scattered randomly. This may seem like an obvious thing to say. Of course, the universe has structure, but the depth of what it means took astronomers decades to fully understand. And even now, even with the most powerful telescopes we have ever built, we are still learning the shape of the place we live in. Tonight, in this chapter, you will get a new address. Not your street, not your city, not even your country or your planet. A larger address, one that locates you inside the structure of the observable universe itself. An address that only received its outermost line 11 years ago, and that may have been updated again in October 2024. Let's start with what the universe looks like from the outside. Imagine a glass sphere roughly 3 feet across, completely filled with soap foam, the kind with large irregular bubbles pressed against each other. Now imagine that instead of air in the foam, the bubbles are voids, regions of near emptiness where almost no galaxies exist. And instead of the thin films between bubbles, there are filaments, long, dense threads of matter along which galaxies cluster like beads on a string. And where multiple filaments cross, where the film walls intersect, there are nodes. The densest regions in the universe where galaxy clusters pile up, and the IGM we discussed last chapter reaches its highest temperatures. This is the cosmic web. It is the largest known structure in the observable universe. It organizes everything. Every galaxy, every cluster, every filament of intergalactic gas into a single continuous pattern that stretches across the entire 93 billion light-years of space we can observe. And the Milky Way is not floating randomly within it. We have a specific address, a specific location, and finding it required one of the most creative acts of measurement in the history of science. Here is the problem. You cannot see a web from inside a single strand of it. For most of the 20th century, astronomers could map where galaxies were, their positions in the sky, their distances, but the pattern those positions formed was hard to read from inside. It was like trying to understand the floor plan of a building by looking at a single brick. The breakthrough came when astronomers realized they could use not just position, but motion to understand structure. In a gravitational landscape, galaxies don't move randomly. They flow. They drift toward concentrations of mass and away from voids, the way water flows downhill toward drains. If you could map not just where every galaxy is, but where every galaxy is going, its peculiar velocity, the motion above and beyond the general expansion of the universe, you could reconstruct the shape of the gravitational terrain beneath. Think of it like watching a crowd from above. You can't see the doors, but you can see which direction people are walking. The doors reveal themselves through the motion of the people. In 2014, a team of astronomers led by R. Brent Tully at the University of Hawaii did exactly this. They mapped the peculiar velocities of tens of thousands of galaxies using radio telescopes, identified the regions where those flows converged, the gravitational drains, and used them to draw the boundaries of superclusters, not by density, by motion. What they found was a structure they named Laniakea. Laniakea, from the Hawaiian lani meaning heaven, and akea meaning immeasurable, spacious, is the supercluster that contains the Milky Way. It spans approximately 500 million light-years across. Let that sit for a moment beside what came before. The local group, our immediate neighborhood of 80 galaxies including Andromeda, spans about 10 million light-years. Laniakea is 50 times larger. It contains roughly 100,000 large galaxies. Its mass is approximately 10 to the 17th power solar masses, 100 quadrillion times the mass of our Sun. Within Laniakea, there are several previously named superclusters. The Virgo supercluster, where our local group resides. The Hydra Centaurus supercluster. The Pavo Indus supercluster. These were once thought to be independent structures. It turns out they are all subregions of the same larger gravitational basin. Neighborhoods inside the same city. The Milky Way sits near the outer edge of Laniakea, not at its center, not at its heart, but on the periphery, near the boundary with the neighboring Pisces Cetus supercluster. We are, in the cosmic sense, suburbanites. On the outskirts, where the flow is weaker, the filaments thinner, the nodes farther away. And somehow, even here, we are part of the web. At the heart of Laniakea is something that had been puzzling astronomers since the late 1970s, the Great Attractor. In 1978, astronomers studying the motion of nearby galaxies noticed something strange. The Milky Way and thousands of neighboring galaxies were all moving toward a single point in space, a point located roughly 150 to 250 million light-years away, in the direction of the constellation Norma, just beyond what astronomers call the zone of avoidance, the region of sky permanently blocked from optical view by the dust and gas of our own galaxy's disk. Something was there, something massive, something pulling at more than 1 million miles per hour. They called it the Great Attractor. For years, it was genuinely mysterious, an unseen gravitational anchor in the one direction we couldn't see clearly. X-ray and radio observations eventually revealed what lay in that direction. The Norma cluster, a massive concentration of thousands of galaxies. Behind it, pulling even harder, the Shapley supercluster, one of the most massive concentrations of galaxies in the local universe. But the great attractor, it turned out, was not a single object, it was a place. The central gravitational focal point of Laniakea itself, not a black hole, not a single massive galaxy. The collective pull of 100,000 galaxies and their surrounding dark matter, converging on a region the size of a small supercluster. Tonight, as you lie still, the Milky Way is moving toward it at approximately 600 kilometers per second, about 1.3 million miles per hour. You will never get there. Dark energy is pushing the outer boundaries of Laniakea apart faster than gravity can pull them together. The great attractor is a destination we are falling toward and will never reach, on a journey that will be interrupted by the expansion of the universe itself. A compass pointing at a place that is, in the longest run, unreachable. Now here is where the story takes a turn that happened just last year. In October 2024, a team led by R. Brent Tully, the same astronomer who named Laniakea, published new results in Nature Astronomy using the Cosmic Flows 4 catalog, the most detailed survey of galaxy motions ever compiled, covering over 56,000 galaxies. Their finding, Laniakea itself, may be only part of something larger. By tracing the gravitational flows of galaxies beyond the boundaries of Laniakea, the team found evidence that the flows don't stop at Laniakea's edge. They continue, pointing toward a more distant concentration of mass called the Shapley concentration, located roughly 650 million light-years away, well beyond Laniakea's boundary. Their analysis suggests there is a 60% probability that the Milky Way belongs to a gravitational basin roughly 10 times larger in volume than Laniakea, a basin centered not on the great attractor, but on Shapley. If confirmed, the address changes again. Laniakea would not be our outermost supercluster. It would be a sub-basin, a smaller watershed within a larger one. The way a river valley is part of a larger drainage basin, which is part of a continental watershed. This discovery presents a challenge, said University of Hawaii astronomer Asen Kurkchi, a member of the team. Our cosmic surveys may not yet be large enough to map the full extent of these immense basins. We are still gazing through giant eyes. But even these eyes may not be big enough to capture the full picture of our universe. The address is still being written. This has happened before, twice now, in living memory. First, for most of the 20th century, our largest known address was the Virgo supercluster, a structure about 110 million light-years across, containing the local group and several dozen other clusters. That felt like the outermost layer. Then, in 2014, it turned out the Virgo supercluster was just one neighborhood inside Laniakea, which was 5 times larger. Now, in 2024, Laniakea itself may be just one neighborhood, inside something 10 times larger still. The pattern suggests a particular kind of humility. Every time we build a telescope powerful enough to see the next layer out, we discover we are smaller pieces of something larger than we thought. Not smaller in value, smaller in address. Located deeper within a structure whose full shape we have not yet seen. Like someone reading a letter who keeps discovering the envelope is larger than expected. Let's ground all of this in something you can hold. The full address, as we currently understand it, goes like this. You are on Earth. Earth is in the solar system, which is in the Milky Way galaxy, located about 27,000 light-years from the galactic center on a quiet stretch of the Orion Arm. The Milky Way is in the local group, a gathering of 80 galaxies spanning 10 million light-years. The local group is near the outer edge of the Virgo cluster, a dense concentration of more than 1,300 galaxies, centered about 65 million light-years away. The Virgo cluster is within the Virgo supercluster, which is itself a small part of Laniakea, spanning 500 million light-years. And Laniakea, if the 2024 data holds, is within the gravitational influence of the Shapley concentration, 650 million light-years away, part of a structure 10 times Laniakea's volume that we have not yet fully mapped or named. That is your address. It took the entire history of modern astronomy to write it, and we are still not sure how many lines it has. What is remarkable, and what I want to leave with you before we move on, is that none of this was obvious. For thousands of years, humans looked at the night sky and saw fronts of light. Just that. No structure, no web, no address. The cosmic web is invisible to the naked eye. It cannot be photographed in a single image. It can only be inferred from the way millions of galaxies move, from the subtle gravitational currents running through intergalactic space, from data gathered across decades by telescopes and radio dishes and X-ray observatories orbiting the Earth. We didn't see it, we deduced it from the inside by watching which way the rivers run. And the Milky Way, it turns out, is not just floating in the universe. It is located. It sits at a specific place in the filaments, near the outer edge of an immense gravitational watershed, falling slowly toward a center it will never quite reach. Part of a structure so large that the word structure barely fits. You are not in empty space. You are somewhere, and the map is still being drawn. In the direction of the constellation Boötes, a constellation named for a herdsman driving his plow eternally around the northern sky, there is a place where the universe seems to have forgotten to put anything. It is called the Boötes Void, and it is one of the most quietly unsettling and quietly beautiful places we have ever found. Before we get there, let's establish what a void is supposed to be. In the cosmic web we explored last chapter, voids are the natural gaps, the bubbles of near emptiness between filaments. They make up roughly 80% of the observable universe's volume. Most of them are between 30 and 300 million light-years across. They are not unusual. They are a predicted feature of the way the universe's structure grew, from small fluctuations in the early cosmos. The same way bubbles form naturally in foam, the Boötes Void is a void. But it is not a normal one. It spans approximately 330 million light-years in diameter. Its center sits roughly 700 million light-years from Earth. In a volume of that size, a sphere 330 million light-years across, the standard distribution of galaxies in our universe would predict something in the neighborhood of 2 galaxies. Dense and sparse patches, yes, but on average, roughly 2,000. The Boötes Void contains approximately 60 galaxies, in a space where 2 should be. It was discovered in 1981 by astronomer Robert Kirshner and his colleagues during a survey measuring galaxy redshifts to map the large-scale structure of the universe. They were not looking for an empty space. They were looking for galaxies, and they simply kept not finding them. Survey after survey in that direction, the same hollow region. A sphere of near-nothing, larger than anything they had seen before. Kirshner's team reported the discovery in the Astrophysical Journal. The astronomical community was startled, not because voids were unknown, but because a void this large seemed to push against the standard models of structure formation. How, in a universe only 13.8 billion years old, had something this empty had time to form? The numbers deserve a moment. The Boötes Void is roughly 0.27% the diameter of the entire observable universe. That may sound small, but the observable universe is 93 billion light-years across. 0.27% of that is still 330 million light-years. If you traveled at the speed of light from one edge of the Boötes Void to the other, the journey would take 330 million years. When the light entering your eyes right now left the far side of the Boötes Void, our ancestors, the organisms that would eventually become modern humans, had not yet appeared on Earth. In the 1980s, astronomer Greg Aldering, studying the void, offered an observation that has never quite left astronomers who heard it. If the Milky Way had been in the center of the Boötes Void, we wouldn't have known there were other galaxies until the 1960s. Let that settle for a moment. The entire history of humanity's discovery that we live in one galaxy among billions, all of that, would have been delayed by tens of thousands of years, simply because of where we happened to be born in the cosmic web. Edwin Hubble's 1920s discovery of Andromeda as a separate galaxy would have been impossible. The telescopes of his era would have found nothing but our own stars and an ocean of dark. Where you are in the universe determines what you can know about the universe. But here is what most descriptions of the Boötes Void leave out, and what I think is the most interesting part. The 60 galaxies inside it are not randomly scattered. They are, according to surveys, clustered in faint filaments and walls within the void. Tenuous threads of structure threading through the emptiness, as if the cosmic web continued inside the void at a much lower density. A ghost web within the void. This is actually what cosmological models predict. Voids are not perfectly empty. They have their own internal structure. Subvoids and mini-filaments and isolated dwarf galaxies clinging to the faintest threads of dark matter. The Boötes Void is not a true vacuum. It is simply a place where the density of matter fell so far below average that almost nothing had enough gravity to pull together into galaxies. A whisper of structure in a space where the cosmic web nearly went silent. Now here is the new science, and it is stranger than the void itself. The galaxies that do manage to exist inside voids are measurably different from galaxies in normal environments. This has been confirmed in several studies published between 2023 and 2024, including work using the Illustris TNG simulation and analysis of SDSS survey data published in both the monthly notices of the Royal Astronomical Society and Astronomy and Astrophysics. Void galaxies tend to be bluer, more actively forming stars, more gas-rich, less evolved, as if they are younger, not in age but in development, less shaped by mergers, less disturbed. In denser regions of the universe, filaments, clusters, galaxies have long histories of interaction. They collide, merge, strip gas from each other, quench each other's star formation. They are complicated, worn, shaped by everything they have been through. A galaxy in a void has been through very little. It formed, drew in its gas slowly, and grew in something close to silence, with no neighbors close enough to disturb it. Its star formation history is slower, quieter, more extended in time. Void galaxies are, in a very real sense, living more slowly. They are fossils of an earlier era, not frozen in time, but moving through time at a different pace. In the Boötes Void, the 60 galaxies that do exist have likely evolved largely undisturbed since they formed. They carry in their chemistry and structure the imprint of conditions from far earlier in the universe's history. They are, some researchers suggest, among the closest things we have to windows into what young galaxies looked like in the early cosmos. One more layer, and this one is personal. You might think the Boötes Void is somewhere out there, 700 million light-years away, in a direction you'll never look toward. And you'd be right that Boötes is far. But here is something worth knowing. The Milky Way is also in a void, not the Boötes Void. A different one, called the KBC Void, or the local hole, named after the 3 astronomers who identified it in 2013, Keenan, Barger, and Cowie. The KBC Void is proposed to be roughly 2 billion light-years in diameter, making it potentially the largest void ever identified, though its boundaries are still under study and its exact nature is debated among cosmologists. It is not as clean as the Boötes Void. Its underdensity is gentler, perhaps 20 to 30% less dense than the cosmic average, rather than 97% less. But it is real, and the Milky Way sits near its center. What this means is subtle but significant. We are not observers looking into a void from outside. We are inside one. We are living in the relative emptiness. And some researchers, including work published in 2024 and 2025, have suggested that the KBC Void may be contributing to the Hubble tension, the persistent discrepancy between different measurements of the universe's expansion rate. Galaxies inside a void experience slightly weaker gravitational pull from surrounding matter. They expand outward slightly faster than the cosmic average. That local expansion rate, some calculations suggest, could account for about 11% of the difference between the 2 Hubble constant measurements that have puzzled cosmologists for years. We live in the emptiness, and the emptiness may be shaping what we think we know about how fast the universe is growing. But here is what I find most peaceful about all of this. Voids are not failures of the universe. They are not places where something went wrong. They are the inevitable consequence of the same physics that built the filaments and the clusters. The same gravitational story, just told from the other side. Where matter gathered, clusters formed. Where matter left, voids grew. The Boötes Void is not an absence. It is a record of how matter moved, of where the currents of the early universe ran and where they didn't. It is a place the cosmic web breathed out and never breathed back in. In the language of structure formation, voids expand. They are the growing lungs of the universe, regions where the residual expansion of space moves slightly faster than average because there is less mass to slow it down. Over cosmic time, voids grow larger and emptier, while filaments grow denser and brighter. The universe is not becoming more uniform. It is becoming more structured, more web-like, with every billion years that passes. Brighter where matter is, darker where it isn't. The Boötes Void will be larger in 1 billion years than it is tonight, and somewhere in that void, 700 million light-years away, in the general direction of the Herdsman constellation just above the northern horizon, 60 small galaxies drift through the near silence, blue, gas-rich, slowly forming stars, living at their own pace in the space the universe left open, quietly, almost alone, but not quite. The distance between galaxies is not fixed. It is growing right now, as you rest, as you breathe slowly in the dark. The space between every unbound galaxy in the observable universe is increasing. Not because the galaxies themselves are moving through space, but because the space between them is stretching, the way the surface of a balloon stretches when you inflate it, carrying everything on it farther from everything else. This is the expansion of the universe, and it is one of the stranger things we know to be true. Let's start with what expansion actually means. In the early 20th century, astronomers began noticing something in the light from distant galaxies. The light was shifted toward the red end of the spectrum, stretched, elongated, the way sound stretches to a lower pitch when the source moves away from you. And the farther away a galaxy was, the more its light was shifted. The most natural explanation: everything was moving away from everything else. The universe was expanding. In 1929, Edwin Hubble published the relationship that now bears his name. The recession velocity of a galaxy is proportional to its distance. Double the distance, double the recession speed. This is Hubble's law, and it has held up across nearly a century of increasingly precise measurements. The constant of proportionality, the number that describes how fast the universe is expanding per unit of distance, is called the Hubble constant, and it is the source of one of the most fascinating unsolved problems in modern physics. Here is the trouble. There are two main ways to measure the Hubble constant, and they disagree. The first method looks at the early universe, the cosmic microwave background, the faint afterglow of light left over from the Big Bang, analyzed by the Planck satellite. From this method, the Hubble constant comes out to approximately 67 kilometers per second per megaparsec. The second method looks at the local universe, measuring distances to nearby galaxies using Cepheid variable stars and type Ia supernovae as standard candles, objects whose intrinsic brightness is known precisely enough to calculate their distance. From this method, most recently confirmed by the S-Series team, using the James Webb Space Telescope in 2024, the value comes out to approximately 73 kilometers per second per megaparsec, 67 versus 73. The difference is about 8%, small in everyday terms, enormous in cosmological ones. By 2025, this discrepancy has reached a statistical significance of 5 to 6 sigma, meaning it is overwhelmingly unlikely to be a coincidence. The measurements appear to be correct. The methods appear to be sound. The numbers simply disagree. This is called the Hubble tension, and it is the single, most persistent, stubborn disagreement in observational cosmology today. What causes it? no one knows for certain. The possibilities include new physics in the early universe that the standard model doesn't account for, the KBC void we discussed last chapter, which may be making the local expansion rate appear faster than the global average. The possibility that dark energy is not constant, but changes over time, or something else entirely that hasn't been identified yet. The universe is expanding. We just can't fully agree on how fast. Now here is what expansion means for the distances between galaxies, and where the story becomes truly strange. Hubble's law says that recession speed scales with distance. A galaxy twice as far away recedes twice as fast. A galaxy 10 times as far recedes 10 times as fast. Follow that scaling far enough, and you reach a distance at which the recession speed equals the speed of light. At that distance, approximately 14 billion light-years, space itself is expanding fast enough that any light emitted by a galaxy there, aimed directly toward us, makes no net progress. It runs in place. Beyond that distance, light emitted today can never reach us. Those galaxies are for all practical purposes gone, not destroyed, not moved, but severed from us by the relentless growth of the space between us and them. This is the cosmic event horizon. It currently sits at roughly 16 to 18 billion light-years away, a sphere around the Milky Way, marking the boundary of what we can ever receive signals from at any point in the infinite future. The observable universe extends to about 46.5 billion light-years, but of that vast volume, only about 6% is actually reachable. Galaxies close enough that we could, in principle, ever send or receive a signal from them. The other 94% is already gone from our future. We can see it. We cannot touch it. The light from those galaxies still crosses the ever-stretching space toward us, arriving as older and older news, redder and redder with each passing billion years, and eventually fading below any possible detection threshold. Right now, as you lie here, hundreds of millions of stars are crossing that line, moving from reachable to unreachable, not with any drama, just drifting, and the universe will keep doing this. In roughly 100 billion years, about 7 times the current age of the universe, the expansion will have moved nearly all of today's observable galaxies beyond the event horizon. The only objects remaining visible will be those gravitationally bound to the local group, the Milky Way, Andromeda, or whatever emerges from their encounter, and the small cluster of dwarf galaxies that will remain tied together by gravity. Future astronomers, if any exist, will look up at a sky that appears nearly empty. Not because the universe is empty, but because all but the nearest galaxies will have drifted beyond the reach of light. There will be no evidence from observation alone that the universe once contained trillions of galaxies. They may conclude, from what they can see, that the universe is tiny and lonely. They will be wrong, but they will have no way to know that. We are living in the most information-rich moment the observable universe will ever have for any observer within it. The sky tonight, with its visible band of the Milky Way and the faint smear of Andromeda and the distant clusters that deep-field images have revealed. This is the universe at its most open, its most knowable. We happen to arrive at the right time. Now here is the newest layer, the one that was not in the picture before April 2024. For decades, dark energy was treated as a constant, a fixed property of empty space, the same everywhere and at all times. This is the cosmological constant that Einstein introduced, and then famously called his greatest blunder, though it turns out to be real. But in April 2024, the Dark Energy Spectroscopic Instrument, DESI, released results from its first year of data, mapping the large-scale structure of the universe using baryon acoustic oscillations, the ancient ripples from the early universe that act as a cosmic ruler. And what those results hinted at was unexpected. Dark energy may not be constant. The DESI data, when combined with supernova and cosmic microwave background measurements, showed a slight but statistically meaningful preference for a model where dark energy changes over time. Weaker in the past, potentially stronger now, or some more complex variation. The signal was confirmed again in December 2024 when DESI released additional unblinded results, strengthening the case. The team was careful. This is a hint, not a proof. Further data will be needed. The Euclid Space Telescope, with its first primary results expected in 2026, will provide an independent test. But if dark energy is not constant, if it evolves, then the future of the universe becomes genuinely uncertain in ways it wasn't before. A changing dark energy could mean the expansion accelerates faster than expected. It could mean the observable universe shrinks in our future faster than current models predict. It could, in extreme scenarios, eventually overcome even the gravity-holding galaxies together. A scenario cosmologists call the Big Rip, though current DESI data does not favor anything that dramatic. What it means tonight quietly is this: we do not fully understand the force that is driving everything apart. We know it is there. We have measured its effects. We are building instruments to study its behavior across cosmic time. But we do not know what it is. The universe is being pushed apart by something, and that something is one of the deepest mysteries in all of physics. There is a thought I want to leave with you before we move on. The expansion of the universe can feel like a kind of loneliness. Everything drifting away from everything else. Galaxies receding into inaccessible silence. The future shrinking, galaxy by galaxy, into a dark and empty horizon. But there is another way to hold the same facts. The local group, our small clutch of galaxies, anchored together by gravity, will survive the expansion intact. The Milky Way, the Magellanic Clouds, Andromeda, Triangulum, the dozens of dwarf companions. Gravity holds them together against the tide. They will drift inward while the rest of the universe drifts outward, slowly becoming a single great structure as the expansion claims everything beyond. What we will lose is the vastness that surrounds us. What we will keep is each other. And even the loss is not quite a loss. Those galaxies drifting beyond the horizon are not destroyed. They continue, their stars burning, their own civilizations, living and ending, and beginning again, their own curious beings looking up at skies from which our own light will eventually disappear. We won't be able to reach each other, but both will still be there. Distance at the largest scales is not separation. It is simply space, growing slowly in all directions, carrying its contents gently into whatever the universe is becoming. In May of this year, just weeks ago, a team of 46 astronomers turned the James Webb Space Telescope toward a faint point of infrared light in a patch of sky near the constellation Eridanus. What they confirmed changed the record books. Again, the galaxy is called MOMZ14. The name comes from its parent survey, the Mirage or Miracle Survey, designed specifically to test whether the surprisingly bright objects JWST keeps finding in the deep early universe are real, or artifacts of some measurement error, mirage or miracle. The astronomers who named the survey knew they were looking at something that, if real, would be almost too strange to believe. MZ14 is real. It has a confirmed redshift of Z equals 1444. A number that, translated into physical reality, means this: the light reaching the James Webb Space Telescope was emitted when the universe was approximately 280 million years old. The universe is 8 billion years old today, which means we are looking back across 98% of all of cosmic time. Its current distance from us, accounting for the expansion of space that has been happening throughout those 13.5 billion years of travel, is 8 billion light years. As of May 16, 2025, MOMZ14 is the most distant galaxy ever confirmed by human instruments. Let's sit with that number. 33.8 billion light years. The observable universe has a radius of about 46.5 billion light years. MOMZ14 sits at roughly 73% of the way to the edge of everything we can see. Not quite at the boundary, but far closer to it than to us. The previous record holder was Jade's GSZ 14-0, a galaxy that existed when the universe was about 290 to 300 million years old. MOMZ14 pushes the frontier back by another 10 to 20 million years, deeper into the universe's first chapter, into what astronomers call the epoch of reionization, when the universe was transitioning from dark and neutral to lit and ionized. Before JWST, the record was held by a galaxy called GNZ111, discovered by the Hubble Space Telescope, from when the universe was about 400 million years old. That galaxy is no longer even in the top 10 on the distance list. JWST has rewritten the record books so thoroughly in 3 years that the frontier has moved more in that time than in the previous 3 decades. But here is what makes MOMZ14 more interesting than its distance. It should not exist, or rather, it exists in a form that nothing in our models of the early universe quite predicted. MOMZ14 is tiny. Its effective radius is approximately 241 light years, making it about 1% the size of the Milky Way. If you shrank the Milky Way to the size of a city block, MOMZ14 would fit in a parking space, and yet it is extraordinarily bright. Not bright because it has many stars. Its total mass is roughly 100 million solar masses, considerably less than even our small Magellanic Cloud. But it is producing ionizing light at a furious rate, actively forming new stars during what the astronomers describe as a burst, a period of intense, rapid star formation that is lighting it up far beyond what its size would suggest. Its nitrogen-to-carbon ratio is higher than that of our Sun. Its chemical composition resembles the ancient globular clusters attached to the Milky Way, structures that formed in the earliest epochs of our galaxy's history and have been slowly aging ever since. In other words, MOMZ14's chemistry looks like something very old, and it is one of the oldest things we have ever seen. The paper announcing its discovery has a title that the team chose deliberately: A Cosmic Miracle. A remarkably luminous galaxy at Bang 1444, confirmed with JWST. They called it a miracle, not as hyperbole, as a precise scientific term, a reference to the Mirage or Miracle Survey, whose whole purpose was to determine whether these improbably bright early objects were real. And this one is a miracle confirmed. MOMZ-14 is not alone in being anomalous. Since JWST began science operations in 2022, it has found roughly 100 times more bright, luminous galaxies in the early universe than theoretical models predicted should exist. 100 times more. The models said, "You will find a handful." JWST found hundreds. Imagine visiting a foreign land and finding that many of the toddlers there weigh as much as teenagers, wrote one Scientific American article describing the puzzle. There is a growing chasm between theory and observation related to the early universe, said Dr. Jacob Shen, a postdoctoral researcher at MIT involved in the MOMZ-14 discovery. What does this mean? It means that either our models of how quickly stars can form in the early universe are wrong, or the early universe had some ingredient, perhaps a different kind of initial mass function for its stars, perhaps bursty star formation cycles, perhaps some role of dark matter that allowed galaxies to build up mass and brightness far faster than we thought possible. The honest answer, in 2025, is that we do not know. JWST is finding galaxies that our best models said should not exist yet, and they do. Something about the first few 100 million years of cosmic history was more vigorous, more efficient, more productive than anyone anticipated. The universe did not wait politely for galaxies to grow. It rushed. Now here is the thing I want you to really feel, because it is the strangest part and also the most beautiful. When we look at MOMZ-14, we are not seeing it as it is. We are seeing it as it was 13.5 billion years ago. The photons entering JWST's mirrors right now were launched from a galaxy that existed before our sun, before our solar system, before the Earth, before almost everything you can name. The galaxy those photons left may not exist at all in its current form. It may have grown, merged, been consumed, transformed into something else entirely over 13.5 billion years of cosmic evolution. We are seeing a fossil of light, not the galaxy, its memory. There is a phrase astronomers use for this: look back time. When you observe an object at a great distance, the look back time is how far back in history you are seeing. For MOMZ-14, the look back time is 13.53 billion years, nearly the entire age of the universe. And here is what makes that strange in a very precise, specific way. The universe was 280 million years old when MOMZ-14 emitted this light. At that moment, the space between that galaxy and the point where JWST now floats was far smaller than it is today. The universe was younger, less expanded, more compact. The light set out on a journey across that relatively shorter distance. But as it traveled, space kept expanding around it, stretching the gap between emission point and reception point, stretching the light itself to longer wavelengths, which is what the redshift measures. By the time that light arrived, 13.53 billion years had passed, and the galaxy that emitted it was now 33.8 billion light-years away. It is like a message sent from across town, arriving years later to find that town has become a different continent. The distance at arrival is not the distance at sending. Both are real. Both are meaningful. They just answer different questions. And what about Mom Z14 now? Where is it tonight? Somewhere out there, 33.8 billion light-years in the direction of the constellation Eridanus, near the southern edge of the winter sky. The descendant of that tiny, bright star-forming galaxy still exists. Or whatever it has become. It has had 13.5 billion years to grow, to merge, to evolve. It may have joined other galaxies, contributed its stars to a larger system, participated in the same cosmic web we have been tracing tonight. We will never see what it looks like now. The light from its present state will not reach us for another 33.8 billion years, long after the sun has died, long after the earth is gone, long after any civilization we might build has concluded its entire history. What we have is the photograph it sent us 13.5 billion years ago. And that photograph, those few pixels of redshifted light, those spectral lines confirming its redshift of 1444, is enough to know it was there, enough to know the universe was already forming galaxies with fierce urgency, almost before it had time to breathe. Enough to push our understanding of the first chapter further back than any instrument in human history had managed before. One more record broken, one more wall pushed back, one more sliver of the dark made briefly, improbably visible. The name of the survey that found it, one more time. Mirage or miracle. The scientists called it a miracle, in the most careful, evidence-based, peer-reviewed sense of that word. Something that, by all prior expectation, should not have been there, was there, shining. We have traveled a long way tonight, and before we turn inward, before we ask what any of this means for us, I want to stop at something that has been quietly beneath everything we've discussed. Something about distance itself. Because distance out here is not what it appears to be. Here is a thought experiment from the Nobel Prize-winning physicist Roger Penrose, described in his 1989 book, The Emperor's New Mind. Imagine two people walking past each other on a sidewalk. One is walking toward the Andromeda Galaxy. The other is walking away from it. Ordinary walking speed. A few miles an hour. According to Einstein's special theory of relativity. Confirmed physics, not speculation. Those two people, standing within feet of each other at the same moment, have different definitions of what is happening right now in Andromeda. Not different by milliseconds. Not different by hours, different by several days. The person walking toward Andromeda has a now at Andromeda that includes events a few days further into Andromeda's future than the now of the person walking away. Same sidewalk, same sky, but their personal slices through four-dimensional space-time, their planes of what counts as the present moment, are tilted slightly differently by their motion, and at 2.537 million light-years, even a tiny tilt becomes a gap of days. There is no single universal now that connects you to a distant galaxy. The present is local. It is personal. It belongs to the observer. This is the first way distance is alive. Here is the second. When we say Andromeda is 2.537 million light-years away, we are giving its proper distance, where it is right now, at this moment, measured by an imaginary ruler stretched across today's universe. That is the most physically meaningful number. But for MOMZ 14, the galaxy we visited last chapter, the proper distance today is 33.8 billion light-years, while the light we received only traveled about 53 billion light-years to reach us. The universe expanded so much during that journey that the Galaxies is now far further away than the distance the light actually crossed. Distance is not a snapshot. It is a process recorded in light that departed long ago, arriving to describe a universe that has since moved on. And here is the strangest layer. You cannot know what Andromeda looks like right now. The most recent light from Andromeda is already 537 million years old by the time it reaches your eyes. Whatever Andromeda is doing tonight, whatever is happening in those trillion stars while you lie here, that information has not arrived yet, will not arrive for 537 million years. You can see the past. You will eventually learn the future once its light arrives. But the present, at any significant distance, is permanently invisible. Everything you see when you look up is already over. Every photon that has ever entered your eyes was emitted somewhere in some history that is complete. The stars in tonight's sky are showing you light from years, decades, centuries, millions of years ago, all arriving simultaneously, all labeled now, none of them actually present. The present is the only moment that cannot be observed. So when we ask tonight's question, how far apart are galaxies, really, and reach for a clean answer, we find something more honest than a number. The answer depends on when you ask, on how you are moving, on whether you mean the gap a ruler would measure today, or the path light actually traveled, or the time since emission, all of which give different numbers for the same galaxy. It depends on what you mean by now, and now, it turns out, is one of the most contested and subtle concepts in all of physics. This is not a failure of measurement. It is a feature of the universe, a deep truth about the nature of space and time that Einstein revealed, and that cosmology has been carefully unpacking ever since. Distance out here is not a number on a ruler. It is a living thing, growing with the expansion of space, bending around mass, shifting with the motion of every observer who tries to measure it. You don't need to hold all of this. No one does. Not in a single lying still in the dark. Even physicists who work with these concepts settle into them slowly over years. What matters is the feeling beneath all the numbers. Distance out here is not a gap. It is a relationship between position and time and motion and the speed of light and the age of the universe and the direction of expansion. It breathes. It changes. It means something slightly different depending on who you are and when you ask. And somehow, in that complexity, in that aliveness, there is something deeply restful, because it means the universe is not a cold, static arrangement of objects at precise, fixed separations. It is a dynamic, living structure, and you are inside it, moving with it, a part of the very fabric that makes the distances what they are. There is no distance between you and the universe. You are part of what distance is measured through. After traveling this far, the question finally turns inward. Not outward anymore, not further, to here. To this moment, to you, lying still, somewhere on this small specific planet. Where exactly are you? Not your street. not your city. The full address: you are on Earth, a rocky planet, orbiting about 27,000 light-years from the center of the Milky Way, on a quieter stretch of the Orion Arm. Not at the galactic center, not at the edge, the suburbs by any reasonable measure. The Milky Way sits near the outer edge of the local group, a cluster of roughly 80 galaxies spanning 10 million light-years. The local group lives near the boundary of Laniakea, a supercluster 500 million light-years across, and Laniakea itself may be a sub-basin within something centered on the Shapley concentration, 650 million light-years away, a structure 10 times larger, still being mapped. You are also, as we discussed in Chapter 6, inside the KBC void, a large underdensity roughly 2 billion light-years in diameter, where matter runs about 20 to 30% thinner than the cosmic average, not at the center of anything, located somewhere particular, unremarkable by cosmic standards, and therefore remarkable in all the ways that matter. Now let's talk about what you are made of. The hydrogen in your body, in every molecule of water, was forged in the Big Bang, not in a star. In the universe's first 3 minutes, when temperature ran into the billions of degrees, and nuclear fusion was happening everywhere at once. That hydrogen is the oldest material you carry, 13.8 billion years old. It existed before any galaxy, before any star, before the cosmic web had taken shape. The oxygen that fills your lungs with every breath, about 65% of your body's mass, was made in the cores of massive stars that died before the sun was born, then scattered by supernovae. According to NASA, all of the oxygen in our solar system comes from exploding massive stars. The carbon in every protein, every cell, every strand of DNA, built by stellar nuclear fusion in red giant stars, through a process so improbable that the physicist Fred Hoyle, who discovered it, said the universe looked like it had been monkeyed with. The iron carrying oxygen through your blood right now was forged in the dying cores of stars more massive than the sun. The calcium in your bones traces back to supernova explosions. The gold anywhere on Earth was created when neutron stars collided. Collisions so violent, they produce gravitational waves, ripples in space-time we have now learned to detect. Every element heavier than helium in your body was forged in a dead star. Every breath is stellar exhaust. Every bone is supernova debris. You are not merely made of the universe. You are made from its most dramatic moments. The violence of the early cosmos is, in the most literal sense, what you are. But here is what I want to add. Those atoms didn't travel directly to you. They drifted through intergalactic space. They became part of molecular clouds. They were incorporated into stars that lived and died before the sun existed. They were expelled, drifted, cycled through the Milky Way for billions of years, and eventually, improbably, arrived in the cloud that collapsed into our solar system, then into Earth, then into the ocean, then into the first cells, then across billions of years of evolution into you. The atoms that make you have crossed distances that rival anything we traced tonight. They have been part of more stars, more clouds, more deaths and rebirths than any spaceship ever launched. You are not a visitor to the cosmos, looking at it from outside. You are a destination, a place where the cosmos arrived. And now the rarest thing. The universe has been doing things for 13.8 billion years. Stars burn, galaxies drift, voids grow. The cosmic web assembles slowly in the dark, and almost none of it, as far as we know, is aware of itself. The Boötes Void does not know it is empty. Andromeda does not know it is approaching us. MOM Z14 does not know it is the farthest thing we have ever seen. The expansion does not know it is stranding galaxies beyond the event horizon. The universe moves. It grows. It evolves. But it does not, as far as we know, notice, except here, except in the places, however rare, where matter organized itself into something complex enough to ask questions, to measure distances, to lie awake and wonder about the gap between the Milky Way and Andromeda. You are that. Whatever that is, aware, curious, capable of wondering. It is not a guaranteed outcome of the universe's history. It is an achievement. Something the cosmos managed to make of itself here, in this brief window of time. So what does your place in all of this mean? It means you are located. You have a real address in the cosmic web, at a specific moment in cosmic time, on a planet that formed at exactly the right distance from a star, enriched by exactly the right generations of previous stars. It means you are made of journeys. Every atom in you has a history longer than the Earth, a provenance that stretches back to the Big Bang through multiple stellar generations, across intergalactic distances, arriving here, briefly, as this particular arrangement that thinks and breathes and wonders. It means you are the universe's capacity to know itself. The atoms in your body are the same atoms that formed in the Big Bang, forged in stars, scattered by supernovae, and eventually, improbably, organized into something that can observe those events, trace their history, and understand where they came from. Without observers, the universe would still expand. Stars would still burn. Galaxies would still drift. But no part of it would know. Tonight, as you rest, your hydrogen-13, 8 billion years old, your carbon borrowed from dead stars, your iron once scattered across the interstellar medium, you are the point where the universe became aware of the distances we have been tracing. Not above them, not outside them. Inside, woven through. Part of what the distance is measured through. After reflecting on our place within all of this, the journey feels as though it is drawing to a natural pause. We have traveled tonight from the kitchen to the cosmos, from a single step across the floor to 33.8 billion light years. We traced the dark matter halos of Milky Way and Andromeda already touching in the silence between them. We found the skeleton of the intergalactic medium, thin, hot, ancient, carrying the memory of the Big Bang in every scattered atom. We stood at the edge of the Boötes Void and learned that we ourselves are living inside a void. We watched galaxies drift beyond the horizon, carried away by something we still do not fully understand. We looked through JWST's eyes at light that left its source before our sun existed, and we found, finally, that you are not a visitor to these distances. You are a destination they were always arriving toward. At each step, the scale grew, and with it, something else quieter, harder to name. The first feeling, when you hold all of this, is release. The distances we trace tonight are too large to carry in the mind all at once, and trying to hold them tightly only makes them slip away. So instead of grasping, let them go. Let the 33.8 billion light years be what they are, out there in the dark without needing you to contain them. Like lying on the surface of the ocean, you don't need to understand the depth to be held by it. The second feeling is perspective. Whatever you are carrying tonight, whatever remained unresolved when you lay down, whatever is waiting for tomorrow, it is real. It matters. But seen from the Boötes Void, from 700 million light-years away, seen from the vantage of a universe that has been expanding for 8 billion years without asking permission, those things take on a different proportion. Not smaller in importance, just smaller in size. There is something quietly relieving about that. The third feeling is belonging. Though the universe is vast beyond any number we used tonight, you are not outside it looking in. You are inside it, made of it, continuous with it. Laniakea is carrying you right now, drifting you slowly toward the great attractor at 600 kilometers per second. The cosmic web holds you in one of its filaments. The KBC void surrounds you. The intergalactic medium stretches outward in every direction from this planet, this room, this moment. The universe is not something above you. It is something you are part of. The fourth feeling is acceptance. There are galaxies whose light will never reach us, distances that cannot be crossed, horizons that will not move. There are questions about Mumsy 14, about what dark energy really is, about whether we are alone, that may never be answered in any human lifetime. At first, that can feel like loss, but acceptance brings something lighter. The recognition that a universe with unanswered questions is not an incomplete universe. It is an honest one, and perhaps most of all, gratitude. To exist at all in a universe this size at this precise moment in cosmic time, when the sky is still full, when the galaxies are still visible, when the chemistry of stars has had just enough time to produce something that can wonder about them, is the kind of improbability that has no adequate word. So what does it mean, in the end, to rest beneath these distances? It means release, letting the vastness be what it is without needing to hold it. It means perspective. Your worries are real, and also very small against 13.8 billion years. It means belonging. You are not outside the universe. You are woven through it. It means acceptance. Not every horizon can be crossed, and that is all right. It means gratitude for this window of time, this arrangement of atoms, this brief and improbable awareness. The distance between galaxies is not empty. It breathes with ancient plasma and dark matter, and the memory of the Big Bang. It is not fixed. It grows, living, expanding every moment. And you are inside it, made of it, a small but conscious knot in the fabric of everything. The galaxies will be there tomorrow. They will be there long after everything we have ever built has ended. For now, simply let your breath slow. Let your body settle into wherever you are. Let the distances hold you, as they always have, as they always will. If tonight's journey found you something worth returning to, Sleepy Science Stories will be here whenever you need it. The galaxies will be waiting. Good night.